Did I talk about the naming the ions? Did we go through all that? All right, so let's talk about the name for ionic compounds. Ionic compounds, you just write the cation name, and then you put a space here, and then the anion name. So all you need to do is know the names for the cation and the anions, which we talked about last time, and then put it together for the name. For molecular compounds, how do we name those? Well, we have a simple set of rules for molecular compounds. These are going to be for the binary molecular compound. Binary stands for what? Two element. Compounds are two elements. And so, for example, CO2, the carbon dioxide. For molecular compounds, we use these prefixes that tell us how many of each. So one carbon, two oxides. If it's not specified. So carbon dioxide. But do we use the prefixes over here, like di, tri? No, we don't use the prefixes there. What if we have something like this, Cl2CO? What would you name that? Cl2CO. Would this be dichlorine monocarbon monoxide? Is that what you'd name it? Yeah. Basically, we don't name this. Why? Because we're restricting this just to binary compounds. Names for this, like ternary, quaternary, those are more complicated. We aren't going to deal with that, except for the ones that we learned with organics, right? But these don't. So we don't worry about them. Well, how do you identify an ionic compound from a molecular compound? Ionic compounds are typically metal and non-metal, but there are exceptions. For example, ammonium nitrate. Ammonium nitrate, is that an ionic compound or a molecular compound? Well, it's all non-metals, so some people might say it's molecular, but we know ammonium consists of NH4 plus and nitrate is NO3 minus. These are ions, so this is an ionic compound, even though it's all non-metals. And so in general, it's metals and non-metals, but it could be all non-metals if there are obvious ions present. How about SiO2? Is SiO2 an ionic compound or is that a molecular compound? Well, on the one hand, silicon is a metal, right? Or is silicon a non-metal? Metallic silicon. Silicon a metal or non-metal? Actually, silicon is at the border between non-metals on the right and metals on the left. And so along this boundary, we call those elements that touch this boundary metalloids or semi-metals. And this has properties of both, non-metals and non-metals and metals. And so with these types of compounds, we can name it either way. We can name it as an ionic compound, which would be silicon 4 oxide, or we can name it as a molecular compound, which would be silicon dioxide. Both these names are common for this, SiO2. It also goes by quartz, is another name. And so things that are at the border can be named using either system. There's a little bit of a movement to get away from this nomenclature system and use this one. You know, the advantage of using this system is we save space. For example, MgCl2, you know, you wouldn't want to call this magnesium dichloride because it's obvious that for every magnesium, which is a 2+, you'd need 2 chlorides to balance out the charge, so we don't have to call it magnesium dichloride. If we called it magnesium dichloride, we're wasting space. Basically, this is not necessary, right? The di. It's pretty obvious. Has to be 2 chlorides. And so that saves paper. You know, we want to save paper. Sure. But, you know, the complication comes when we have something like this, you know, KNA2PO4. You know, how would you name this? Well, is this an ionic compound or a molecular compound? It's an ionic compound, so we would name it potassium disodium or just sodium? Potassium sodium phosphate. But if you heard potassium sodium phosphate, then you can't tell if there are 2 potassiums and 1 sodium or 1 potassium and 2 sodiums. And so is it 2 to 1 or 1 to 2 ratio? Can you tell using the regular ion? No, you can't. And so a particular ionic compound like this, you have to use the molecular nomenclature, otherwise it just doesn't work. And we call this potassium disodium phosphate. Potassium disodium phosphate makes it clear and easy to understand what it is. So there, in that case, using prefixes clears things up. So this is sometimes done. You'll see it like trisodium phosphate. You know, you don't. Trisodium phosphate is just sodium phosphate. But trisodium is just to say you have 3 sodiums on there. And that's because we could have mixed cation salts. Also, we could have mixed anion salts where there's a mixture of anions, you know, chloride, bromide, incorporated in the crystal. And so those are some special cases there. Otherwise, nomenclature system is the same as you've done in Chem 4. So we have ionic, molecular, and next thing we'll name are acids. You know, acids, the cation's always the same. The cation's H+. The only thing that changes for acids is the anion. And so acid names are based on the anion name. And so if we look at the anion, there are only 3 anion types: the ide, the ate, and the ite. And so based on this, we name our acid. If the acid has an anion that ends in ide, we use the hydro prefix in the ic acid ending. If it ends in ate, we just use the ic acid ending. If the anion ends in ite, we change the name of the anion to aus acid. And there are only 3 scenarios that come up, so these are not too difficult as long as you know the anion name. Sometimes you modify the spelling. So sulfate should be sulfic acid, but historically it's been called sulfuric acid. Phosphate should be converted into phosphic acid, but it's phosphoric acid. So sometimes you modify the name of the anion. Otherwise, you just leave it as is. So acids. And what else do we have? Hydrates. Have you done hydrates? Pentahydrate or 5-hydrate. Okay. That's about it for the nomenclature. So just go through and review those. Basically, we're getting the name from the formula. The formula is just its chemical composition. That's what we get. And the chemical composition is, it's going to be an atom or mole ratio. Just moles of atom ratio. And so, you know, the composition of the water is H2O, 2 atoms of hydrogen, or 2 moles of hydrogen for every 1 of oxygen. So that's it. But where do these compositions come from? And so, is tap water pure H2O? Now, tap water is a mixture. There are minerals dissolved in there and other stuff, gases, whatever else. So this is not pure H2O. If I wanted to figure out what is the composition of the liquid, right? You know, I could figure out the composition mixture. You know, how many ppm chloride, how many ppm magnesium, how many ppm this, you know, in this mixture. It's not so huge for some of those. But let's say I separate out, you know, using physical separation methods, and then, you know, get pure water. This process is called purification. You know, what we do is do something like reverse osmosis or distillation or some other technique to generate pure water. Now I have a pure substance here. I want to figure out what its composition is. How can I figure out the composition of this? Well, one way we talked about earlier is just testing some of its properties. What's its boiling point, melting point, freezing point, density, etc., and then matching those. If those match with water, we could say, yeah, should be water here. But if we don't use those properties, how can we figure out what the composition of this liquid is? Let's say this is an unknown liquid. I want to see, you know, what is this unknown liquid made out of? You know, and so the first step is to purify, to make sure it's not a mixture, and then what we do is we do something called a chemical analysis. And so this is composition analysis. So composition determination. There are different types of chemical analysis we can do. You know, for example, we could do sulfate analysis. So sulfate analysis will figure out how much sulfate is present in there. And then we figure out other things that might be present. Alternatively, we could do something called an elemental analysis. Rather than sulfate, you determine how much sulfur is in there, how much oxygen is in there. From the sulfur and oxygen ratio, you could figure out, oh, that must be a sulfate, maybe. But, you know, one type, you know, many types of chemical analysis. One type is called elemental analysis. And rather than looking for species like sulfate, we're looking for elements, the elemental composition. So when they send up a probe to the moon or something, or one of the landers, they figured out the elemental composition of some of the rocks and minerals on the surface of the moon by using some instrumentation, like an XPS. XPS stands for X-ray photoelectron spectrometer. Basically, they blast the rocks with X-rays to knock off core electrons. If you knock off a core electron, one of the valence electrons will come down and emit light. And depending on the frequency of light, you can figure out what element you're dealing with, because each element will emit different frequencies of light and it gives off a fingerprint. And so they can figure out what elements are present in that sample. And so that's just one technique. There are lots of other techniques for elemental analysis. And so if you had a sample like this, one of the things you could do is there's labs specializing in this elemental analysis. And so there's one in Gardena that I've used before, where you send out a sample and you just check what elements they want to test for. You don't want the whole periodic table. It just costs way too much money, right, to test for all those. And so you figure out what all could be present in here, and then you check off those and have them analyze it. And so here we'll check off some elements, maybe hydrogen, oxygen, and some others that might be present, calcium, whatever, sodium. send it out for analysis, and it comes back. Okay, this comes back, let's say this came back at around 11, 12% hydrogen, 88% oxygen. Oh, it's 12% hydrogen, 88% oxygen. What is it? You recognize that composition? You probably don't recognize that composition because what they give you from an elemental analysis is the percent composition by mass. And so what they do is they weigh out a sample and figure out how many grams of hydrogen are in that and how many grams of oxygen, and just take a percentage, you know, grams of hydrogen over total grams times 100%, that's percent hydrogen by mass. And so if we got 88% oxygen and 12% hydrogen, then, you know, I recognize that as water. You know, they'll probably give you a lot more sig figs so you can narrow it down. But since we're not used to that, because percent compositions by mass, you know, atoms weigh different things, and then you got this isotopic ratio distribution, you know, so it's much easier dealing with formulas, you know, and these nice whole numbers. These nice whole numbers is because atoms, you know, you can't have a fraction of an atom. You got to have the law of multiple proportions, that is simple whole number ratios. And so it's terribly inconvenient to represent chemical compositions of elements, not elements, of substances using percent composition by mass. And so we convert these into what? Into formulas. And so we take a percent composition by mass, we assume 100 grams, right? Assume 100 grams, and then we get the gram composition, and then we convert this to moles. And then we get a formula. The empirical formula is the simplest whole number ratio, mole ratio, or atom ratio, which is ratio. And so when we convert that 88 grams of oxygen to moles, 12 grams of hydrogen to mole, and we see the mole ratio is just going to be H2O, water, H2O. All right, that's your standard. I think everybody's done this in Chem 4. And so we'll look at some specific techniques. For example, one of the elemental analysis techniques is called combustion analysis. Okay, we get this from the lab report. They sent us a report. The advantage of combustion analysis is it's inexpensive. You know, the equipment is easy to make. You don't need really any sophisticated stuff except a very sensitive balance. And so the disadvantage of combustion analysis is your sample has to burn. You know, if your sample does not combust, then it's not going to work, right? And so primarily this is limited to mostly organics. You know, organic chemicals tend to be flammable. And so let's take a look at combustion analysis in some more detail here. So we have these organics. And the simplest organic would be like a hydrocarbon, CX, HY. And you burn this in excess O2, and what do you form? You're going to form CO2 and H2O. Then you pass the flow of gases through a desiccant. The desiccant sucks up the water. And so you weigh the desiccant before combustion, and then you weigh the desiccant after combustion, assuming the desiccant has captured all the water. You know, the mass increase of the desiccant will equal how many grams of water was captured. And so if we have that information, then we can figure out how many grams of water captured. And so we go from grams of water. And then we know that all the hydrogen in our original unknown ends up in water. And so we go from grams of water to moles of water to moles of hydrogen, and moles of hydrogen to grams of hydrogen. Actually, you know what? I don't want to go to grams of hydrogen because is a formula gram or mass ratio? No, a formula is going to be a mole ratio. So I want to stop here, figure out how many moles of atoms we have. And then carbon, we can trap the CO2 using a CO2 trap. A CO2 trap usually consists of some hydroxide. Hydroxide loves to capture CO2. And the increase in the mass of the hydroxide would be equal to the grams of CO2 that were captured. And so from the carbon, we go grams of CO2, all the carbon in our original unknown ends up in CO2, so we'll convert that to moles of CO2. Moles of CO2 will go to moles of carbon and stop here. And then we'll just get the mole ratio, the simplest mole ratio, simplest whole number is the empirical formula, or the formula, the composition of this stuff. Okay, then we can go on to CHO compounds, X, Y, Z. Combust these. When we combust CHO compounds, it's a little bit more complicated. The third element in there, we're going to add XSO2. So all the carbon ends up in CO2, all the hydrogen ends up in water. But the oxygen we lose track of. And so basically this is good for carbon and hydrogen here, as far as the determination goes. And so, again, we can go from grams of water to moles of water to moles of hydrogen to grams of hydrogen. Here we have to go to grams of hydrogen because this is how we're going to determine how much oxygen was formed. And so we don't stop at moles. And so we're going one step farther than normal. And so we'll go grams of CO2 to moles of CO2 to moles of carbon to grams of carbon. All right, the reason we had to go to grams is because of this. We can weigh the whole thing here. And so we know how many grams of CHO we have. So if we have grams of CHO minus the grams of the hydrogen, minus the grams of the carbon, we're going to be left with grams of oxygen. And so with grams of oxygen, then we can go to moles of oxygen. And then we can reverse these, here. What we need to do is to go back from grams back to moles. So we'll just get moles of hydrogen here, we have moles of carbon here. And so once we have moles of carbon, moles of hydrogen, and moles of oxygen, then we can just get the mole ratio. And the mole ratio should be the formula, whole number mole ratio formula. If we have a CHS, sulfur instead of oxygen, then it's very similar. We burn this in O2, excess O2, and we're going to generate CO2 plus H2O plus an oxide of sulfur, probably sulfur dioxide or sulfur trioxide, depending on the conditions. And so if we trap these three, then method one would be grams of CO2 eventually to moles of C. And then grams of H2O eventually leads to moles of hydrogen. And then we are going to have grams of SO2 or SO3, depends. And this is going to lead to moles of sulfur. And then just get the mole ratio here. This is method one. We're going to have a trap that traps the sulfur, the oxide of the sulfur. So method one. Method 2 would be just like we did for oxygen over there. In other words, what we're going to get is grams of CO2 to grams of carbon, grams of H2O, eventually leads us to grams of hydrogen. And then we have grams of CHS minus grams of carbon minus grams of hydrogen yields grams of sulfur. From grams of sulfur, we could get moles of sulfur. And then eventually we have to go back here to generate moles of carbon and go back here to generate moles of hydrogen and then just get the mole ratio. That's it. Sometimes we need different reactions. We just can't just do combustion alone. So CHN, we do combustion. Those two typically will form CO2 plus H2O plus oxides of nitrogen. You know, it depends on the conditions also. The NOx. You know what NOx are? NOx, you know, this equals, it could be N2O, you know, where X is 1/2. It could be NO, where X is 1. It could be NO2, where X is 2. And so this is nitrous oxide, nitric oxide, nitrogen dioxide, or dinitrogen monoxide, nitrogen monoxide, and nitrogen dioxide. These are what we call NOx here. And so we get some mixture depending on the conditions. Well, here for CHN, we do two reactions. And so here's reaction 1. Reaction 1 gives us carbon-hydrogen percentage. Here we get, eventually what we want to get is the percent carbon and the percent hydrogen. And so we have to do an additional step, because in the next reaction we aren't going to weigh out the same amount. In the next reaction we take another sample of the unknown, CHN, and subject it to a series of reactions which converts the nitrogen in our original sample to N2 gas. And so from the N2 gas, we can get the percent nitrogen. Okay, from the percent comp, we can go to the formula using the method earlier. And the reason is because we aren't using the exact same sample and we aren't using the exact same sample size, so we need to get something that's, you know, a intensive property that is independent of the amount. And what's independent of the amount would be moles is extensive, grams is extensive. What's independent of the amount would be percent, right? Then we don't need the amounts. Exactly. So this is a little summary of combustion analysis here. And that leads to analysis of an unknown to get its composition. There's some stoichiometry problems, you know, using the mole concept here, gram to mole conversions, that kind of stuff. It's presented in chapter 3. We're going to go to chapter 4 next. Chapter 4 deals with stoichiometry. Stoichiometry are just quantity relationships in chemistry. Typical stoichiometry map. Well, you know, when we look at chapter 4, the first part of chapter 4 is balancing chemical equations. Balancing the equations, just time consuming, not necessarily difficult. Sometimes you get unlucky and have to grind through it, but eventually you'll get the answer. But stoichiometry, once you have that balanced chemical equation, then we can do a mole-to-mole conversion. So we have moles of A, and we want to convert that to moles of B. As long as we have the balanced chemical equation, we're okay. Balanced chemical, or the formula. You know, the formula can tell us the mole ratio also. Anything that gives us the mole ratio will work here. These are moles of A to moles of B. In Chem 4, the most common type of problem you did was you went from grams of A to moles of A to moles of B to grams of B. Gram to mole conversion, mole to gram conversion. So this is a difficult problem. In Chem 1A, it should be more complicated, right? So what could be more complicated? Sometimes you have a mixture, and so you got grams of mix. Sure. And this mixture contains A, right? And so if we have 100 grams of mixture, then what we need is we need the percent of A by mass. In other words, the percent composition by mass. And so if we have 100 grams of mixture and 20% was A, then that means 20 grams of pure A per 100 grams of mixture. We can figure out grams of A. Sometimes we have a volume, you know, of A. If we have volume of pure A, then we need the density, right, to go. Sometimes we have the volume of the mixture, then we would need the density of the mixture to figure out the grams of mixture and then go that way. Sometimes we could go straight into moles of A. You know, going straight into moles of A is if we have the volume of solution A and we have the molarity. How many moles per liter? And we can go straight to moles. So those are some variations. The same thing here, you know, we can go to mixture or wherever branches off to. And so looking at this chapter, like the first part deals with balancing equations. You know, when you're looking at chemical reactions, you look for clues that there was a reaction. Here, it's pretty obvious. We've got some kind of precipitate there. Normally, if a precipitate's generated, you try to write down the color and the form. You know, there's powdery precipitate, cloudy precipitate, coagulated precipitate, flocculent. It's not very dense here. A color change, formation of a solid, evolution of gas, heat. You know, if it gets hot or if it cools down is an important indicator of reactions. So this is a double replacement style reaction there. This one here with the penny, this is a redox reaction. This is a penny and nitric acid. See how it's turning green here. This is a combustion reaction here, burning steel wool, which is steel wool is iron, so just burning iron in there. So here is conceptual, you know, we balance by individual molecules or moles of molecules in this case. Just balancing, tips, balancing. Sometimes the reaction conditions are specified, like delta. Delta means heat. But sometimes you have to be more careful, because not just any elevated temperature, but specific temperatures like this one. 350 degrees C, 340 atmospheres with zinc oxide and, what's that called? Dichromium trioxide or chromium 3 oxide? Chromium 3 oxide. These are catalysts. They aren't actual reactants. So under these conditions, carbon monoxide and hydrogen, two inorganic chemicals, can produce an organic molecule, methanol. Here's an example of redox. That was a redox reaction there. There's another redox, combustion of hydrogen. Potentially very violent redox reaction. Here's a standard stoichiometry problem here. Let's take a look at some of their examples. Not this one. This one. An alloy used, alloys are homogeneous mixtures, solid mixtures of metals. Used in aircraft structures consists of 93.7% aluminum, 6.3% copper by mass. The alloy has a density of 2.85 grams per cubic centimeter. 0.691 cubic centimeter piece of alloy reacts with an excess of HCl. How much hydrogen is obtained. And so they give us the volume of the alloy, 0.691 cubic centimeters of alloy. And from this, we can get grams of alloy using the density of the alloy, which is given 2.85. From grams of alloy, we can go to grams of aluminum because we have the percent composition by mass, 93.7 grams of aluminum for every 100 grams of alloy. For grams of aluminum to moles of aluminum, to moles of hydrogen, we need the balanced chemical equation, which is not shown here, but you're going to have to get that. And then from moles of hydrogen to grams of hydrogen. And so just a standard stoichiometry problem with a mixture. It doesn't have to be a solid mixture, it could be a liquid mixture too. For example, this is HCl and water, hydrochloric acid solution. There's a 28.0% HCl by mass. And so for every 100 grams of hydrochloric acid, 28 grams of that is pure HCl, 28.0 grams pure HCl. And they give us the density here, what volume of the solution is required to react completely with 1.87 grams of aluminum in this reaction. So grams of aluminum, moles of aluminum, moles of aluminum, moles of pure HCl, moles of pure HCl to grams of pure HCl. And then once we have grams of pure HCl, we can figure out how many grams of solution we have based on that percent by mass composition. And from grams of solution, we can get milliliters of solution based on the density. And so another kind of standard stoichiometry type problem here. We have molarity. With molarity, we can go straight to moles. Molarity is defined as moles per liter of solution, moles of solute per liter of solution. Inserted in here is something that we have to do in lab, and that is solution dilution. Sometimes we have to take a more concentrated stock solution like HCl and dilute it, like we did yesterday. Yesterday the HCl stock solution was a little too concentrated for a wash, so we diluted it. Well, here, if you want to do a more precise dilution, you use this. This thing's called a volumetric flask. It's a 250. The 250 milliliter volumetric flask is good to 250.00. So actually it's 5 sig figs, although they don't show 5 sig figs here. You automatically know it's 2 decimal places of precision. And so here, we take the concentrated, add some volume, and then just dilute it with water to make them more dilute. And with this, if you want 250.00, you fill it to the mark. And so here they're mixing before filling, because once you fill it with this part of the neck, it's hard to mix. So they're showing the mixing step in between there. The solution dilution equation is this, the M initial, V initial is equal to M final, V final. And so we take a portion of the concentrated and then dilute it with water. Here, the number of solute particles on the left side, and on the right side are the same. So the number of solute is the same, just the volume's changed here. And so solution dilution, this is more a practical component of chemistry. It's not real stoichiometry. Here's another solution dilution example using pipettes. You got to get good at using pipettes. So you pipette a volume over here, and then dilute it with water. Mark. You can't overshoot this, because if you overshoot it, then you don't know what the concentration is. There's only one mark on there. Okay, and then as we take a quick preview, we have limiting reagents. You guys remember how to do limiting reactant problems? I do the smaller amount method versus the comparison of moles. The smaller amount, which one gives a smaller amount of product? That smaller amount of product is called the theoretical yield. And so in conjunction with limiting reactant problems, we do this. Theoretical yield is the yield based on the limiting reagent. The actual yield is what you actually got in the experiment. And percent yield is how close you got to the theoretical yield. The actual yield divided by the theoretical yield times 100%. So we have that. Percent yields are important, because they just tell you how much loss you had. For example, if you got a 95% yield, then that means you lost 5% of the product. It's hard to capture every little crystal, Sometimes it's just not worth it. One little crystal is not going to make a huge difference versus using too much wash solution to get it over. But sometimes you have to be very careful because, oops, I skipped this section here, because of sequential reactions. Let's say you have a series of 3 reactions, and if you lose some product here and you lose some product here, by the end of the series of reactions, you might have very little product. And so some synthesis requires like 12 steps, or more. And so if you get 90% yield in each, you aren't going to be left with 90% product. You're going to be left with way less than 90% yield of final product that you're losing. So you lose some here, and then you're beginning with less here. So by the end of this reaction, your yield is kind of low. So you have to be careful. This is called consecutive reactions. You have simultaneous reactions too. We'll talk about a bit later. And so that's pretty much the chapter. This chapter is all review, I think. So let's take a look at some of the problems that you'll encounter, and then maybe look at some of the chemistry that we have here. And so the first part is just balancing equations. Actually, I forgot. I was going to see. We're going to 325. I'm a little bit ahead, so I can do a couple more examples for you. I want you to name this guy here, Fe3O4. Name that one for me, Fe3O4. Well, I'll let you name that later. Let's move on to, you can think about it a little bit. Let's see, number 18 here too. Take a look at number 26. Number 26 is just a straightforward stoichiometry problem. But the reaction is kind of an interesting reaction. Aluminum metal plus, what's the name of this? NH4ClO4. What is it? NH4ClO4 is called ammonium perchlorate. Good. Would you be able to predict those products? What type of, is that a single replacement reaction? Double replacement? What kind of reaction is that? It looks like a single replacement, but do those products look like the single replacement pattern, A plus BX? No, not at all. And so a lot of reactions, although you'd like to be able to predict everything theoretically, a lot of reactions are you just mix it and see what happens. sometimes you adjust the conditions, you know, and then as you change the temperature, what happens? As you change this, what happens, right? And so here, you know, did you do the yellow flame experiment in Chem 4? Yellow flame means it's starved for oxygen. That means the limiting reagent is oxygen, the excess reagent is methane. And you end up getting a mixture of products. You know, we have our incomplete combustion products like soot, like carbon monoxide. And so in this yellow flame, I want you to do stoichiometry. I want you to tell me how many grams of soot and how many grams of carbon monoxide I'm going to get for every gram of methane that I combust. Is that going to be easy to do? I want you to calculate it theoretically for me. Is that easy to do? No, what's much easier to do? What's much easier to do is just do it under these conditions and then see what forms, right? Well, a lot of these reactions are like that. A lot of these reactions are, you know, depends on the conditions and change what you get, and so you just mix it together and see what happens. But what we want to do is we want to add some additional insight into this. So if I have aluminum solid and ammonium perchlorate, what we want to think about is, you know, what can we understand about these two chemicals, you know, based on the composition of those. And so the first thing we did in analyzing formulas, compositions, is to determine the oxidation state. And so if we look at the oxidation state of aluminum, what is it here? It's 0. Well, oxidation states are important for redox reactions. Redox reactions, we're looking for electron poor and electron rich species. And so aluminum with a 0 oxidation state means it's electron poor, electron rich, or just neutral. You'd say neutral because 0 just seems neutral, right? But here's where you have to have some factual knowledge in addition to, you know, the numbers. And the factual knowledge is metals. What would you say in general about metals and electrons? Are the electrons tightly held or loosely held in metals? Loosely held. So, you know, normally when we think about metals, we think of electron rich, even if the oxidation state is 0, because aluminum is quite capable of losing 3 electrons to form aluminum 3+, right? Sodium is quite capable of losing 1 electron to form sodium+. And so metals are electron rich. In fact, one of the properties of metals is that they tend to lose electrons in chemical reactions. Well, electron rich species, are those called fuels or are those called oxidizers? Fuel is electron rich species the fuel or the oxidizer in redox? The electron-rich species is called the fuel. And so there's a picture of, at the beginning of this chapter, there's a picture of that steel wool being combusted. Well, what's the fuel? Steel, the iron metal. What's the oxidizer? Air, or O2. And so this is thought of as the fuel here. So, well, ammonium perchlorate consists of the ammonium ion. Ammonium has a positive charge here. A positive charge means it's electron rich, electron poor, or just kind of neutral. Electron poor. You would think it's electron poor, but you can't tell by the net charge. Especially for a monatomic, you can. You know, if it's a monatomic, but this is polyatomic. So we can't really tell unless we do the oxidation states, because we need to see what the individual charge on an atom is, because it depends on where that charge is. Is the positive charge on the nitrogen or is the positive charge on the hydrogen? It makes a difference in behavior. And so let's take a look. When we assign oxidation states, how does this work? Yeah. hydrogen goes first at +1, that means nitrogen is -3. Now hydrogen at +1, is that all that unusual? No, the water has hydrogen as +1. Water's no big deal, right? Stable. But nitrogen at -3 means, we'll take a look at the periodic table. Nitrogen with -3 means it's got a full octet of electrons. So we'll call that electron rich, maybe, compared to. And so, will ammonium burn? What do you think? Will ammonium burn? Is it good fuel? Can you burn ammonium ions? Yes, you can burn ammonium ions. You know, methane has carbon in the -4. Methane's a great fuel, right? And so here, this is electron rich. We say ammonium is electron, not poor. We say it's electron rich because of nitrogen, not because of nitrogen. How about perchlorate? What goes first, chlorine or oxygen? Usually the more electronegative element gets assigned first unless it's hydrogen or group 1. And so oxygen should go first at -2, what it likes. Oxygen at -2 is happy as is because think of water, you know, water has oxygen at -2. It's not really electron rich. Is water an electron rich fuel? No. I mean, how easy is it to burn water? No. Water is quite stable. Well, that means chlorine must be what? Chlorine is what charge, oxidation state? Close. You know, -8 plus 8 gives us 0, but it's supposed to add up to -1 plus 7. Which means, take a look at the periodic table. If chlorine's +7, then what happened to chlorine? It lost 7 electrons. Well, how many valence electrons does it have? 7, so it's lost all its valence electrons. Do you think chlorine's going to be happy? No. Chlorine's going to be terribly unhappy, and chlorine is going to be quite electron rich or electron poor. Yeah, extremely poor, right? And so when we look at perchlorate, I see a danger, you know? It's dangerous because it's so electron poor. In other words, species that are electron poor are called oxidizers. And perchlorate is a powerful oxidizer because it's so deficient in electrons. Even though you might say, wait a minute, you know, perchlorate has a negative charge, that means it has an extra electron. Well, unfortunately, that extra electron went to oxygen, not chlorine. So oxygen's happy, but chlorine's terribly unhappy. In fact, even without the aluminum here, I see danger in this. Because, you know, this room has a powerful oxidizer in this room, O2, right? Powerful oxidizer, but I'm not worried. Even though we have a powerful oxidizer, I'm not worried because there's no good reducer to react with it. There's no good fuel to burn in this room, right? But, you know, if I fill this room up with methane, you know, methane has carbon in the -4 oxidation state, then that's good fuel. I'm still not worried yet, because if I fill this room up with methane, you know, I need a little bit of temperature or a spark, right, to get an explosion. Hopefully nobody lights a match or does anything like that. Then we're okay. That's called metastable. You know, it's metastable. You know, it's ready to explode, but not quite there because it needs a little push to get it to explode, right? Well, that's the same thing with ammonium perchlorate. This stuff is metastable. Why? Why? Because you have a powerful oxidizer and a powerful reducer in the same compound. And so if you have a you know, a powerful oxidizer and a powerful reducer right next to each other, why don't they just react? Why? It's because it's a solid. What do we know about solids? Solids, the ions should be in their correct position, right? There's no translational motion. Well, what happens if we heat up that solid and you get it to melt or get it hot? If we get it hot, you know what could happen? One of the ions could collide with the other ion and we get a reaction. We get a reaction because perchlorate wants electrons, ammonium has electrons to give up. Now if we throw aluminum into the mix, then aluminum is a great reducer because metals have electrons that are easy to pluck off. Very easy to pluck off. And so this is a powerful reducer. So we got two fuels and one oxidizer. We don't need any O2 in this, right? In fact, we don't need any aluminum in this. The conditions are right. And so this stuff is what we call metastable. Metastable stuff is fine as long as, you know, there's nothing to trigger it. But sometimes, this happened in Nevada recently. Let's check this out. This was not too long ago. It's a huge...
Ooh, that's gonna be loud.
They're far from that. Wow. This is a huge plant, ammonium perchlorate plant in Nevada that exploded, destroyed the entire plant. So we could use oxidation states to give us insight into, you know, redox properties of these things here. Since I have this up here, do you know what the worst, you know, that's a pretty bad accident, right? I don't know how many people were killed in that one. It wasn't a huge number of people, but I think there were like a number of people who were killed in that. But do you know what the worst industrial accident in the U.S. was? The worst industrial accident in the U.S. was in 1947, and it happened with this. What's the name of this stuff here? Ammonium nitrate. And we know ammonium is electron rich. How about nitrate? What can you tell me about nitrate? Well, what are the oxidation states? +5, good. +5 for nitrogen, -2 for oxygen. And so take a look at the periodic table. That means one nitrogen has a full octet of electrons, the other nitrogen has one nitrogen has a full octet of electrons, 8, and the other nitrogen has nothing. Lost all 5 of its valence electrons. You think this is a happy compound? No. it's okay because maybe, you know, it's in the solid state, room temperature. Maybe that's okay. But this is what we call meta-stable. You know, it just needs something to give it a little kick and it'll react. Because if there's a tug of war, you know, nitrogen versus nitrogen, it's going to happen. Although those two nitrogens aren't exactly equivalent, but you know, this just doesn't look like a very stable situation. You know, give 8 electrons to this side and no electrons to that side. Is that fair? It costs energy to do that. You know, it's called voltage. When you pump electrons on one side and leave the other side a deficit, we generate a voltage. This is a high voltage. High voltages, are those stable? Oh, and things will want to balance out. And so in the chemistry class, we should learn some, you know, this is how you get an idea of what these numbers mean. You get an idea of what these numbers mean by looking at the numbers and then looking at some experimental, you know, data to see, or put it into perspective. And so let's go to, the one I want is not, it used to come right up, but how do I go to history? Is there history on this? Just looked at it this morning. On the right side? Oops, I'm gonna do that. Recently viewed ones? Oh, here it is. And signed out, okay. Does anybody know? Oh, here it is. Browsing history. Does somebody know Internet Explorer? I guess maybe it just cleared it. Shoot. Alright, 1947, Texas City. Part 1. There used to not be so many videos, but now there's so many videos. One news anniversary. No, it was color. I don't know why it's not coming up. All right, I give up. I'm gonna just show you this one of these. Let's just pick this one. Texas City.
You can't spend much time in Texas City with all the big ships that come and go, the oil and chemical refineries, the pipelines and storage tanks brimming with flammable products. You can't spend much time here without thinking the unthinkable. Could it happen again? Could Texas City be another boom town in the worst possible way? 50 years ago, Texas City burned its way into the nation's conscience. The worst industrial accident in American history made Texas City synonymous with disaster. The day it happened, Will Lane was very near the epicenter.
It was hard as rain. I'm really glad to be alive.
Lane was a young chemist at the Monsanto chemical plant. He remembers seeing the bright orange smoke from a burning ship. Firefighters were busy pouring water on the French freighter Grand Camp at the city docks across from the Monsanto plant.
You could look at it, it was real pretty to watch. And there were townspeople by the hundreds that lined the part of our parking lot that was nearest to the ship. They came down to watch a fire.
Texas City had a new fire truck, and this was its first day out. 27 firemen were on the docks trying to put out the fire. The burning ship was so hot, the water around it was boiling. But as a chemist, there was something about that orange-colored smoke that worried Will Lane.
We get to see bits and pieces of paper bagging going up through the air and away. And our boss thought, and I thought too, that we were witnessing a nitrate fire. But someone had said, it's a grain ship when the grain is on fire.
So believing it was only a matter of time before the fire was out, Will Lane went back to work at the Monsanto lab. But the fire was growing hotter, and the orange smoke was attracting an even larger crowd along the docks.
It was a very, very strong sulfur in the air, sulfur fumes.
Herb Metzger watched the fire while talking to a group of high school kids.
This smoke was just a beautiful orange.
Mary Hunter, a Monsanto secretary, was watching from her office window.
And across town, Mrs. Knappenberger, a housewife with a home camera, came here to the Texas City dike to get a closer look at the burning ship. She didn't know it then, but she was about to record America's greatest man-made disaster.
The ship had been loaded not with grain, but with ammonium nitrate fertilizer, the same ingredient that would be used years later in the Oklahoma City bombing. The Texas City blast was so strong it registered as an earthquake in Denver, 900 miles away. It created a tidal wave that washed a barge into a parking lot. 2 airplanes circling the ship were blasted from the sky. Flying debris punctured chemical storage tanks, creating an even larger inferno.
They have another truck up here off of the road. It had about 10 or 15 men, and they were all crushed.
The explosion killed at least 581 people, including school children who had come to watch the fire. But the danger was far from over. Tomorrow, we'll hear the stories of survival and courage from the people who were there 50 years ago. Charles Hadlock, 11 News, Texas City. The Go. Charles Hadlock. This is Charles Hadlock. Texas City has tried to outlive its past, but it's hard. There are so many reminders. An anchor here, a propeller there, and sad, sometimes painful memories all around.
Even today, 50 years later, the tragedy is not forgotten. 6th Street, the once busy main street of Texas City, has been renamed the Street of Memories. For it was along this street that so many screamed and ran for their lives.
The explosion of the French freighter Grand Camp left an entire town dazed and confused.
And I ran as fast fast as hard as I could.
There are many stories of survival. Dr. Will Lane was in the Monsanto lab. He had been watching with suspicion the bright orange smoke of the burning ship docked next to the plant when it suddenly exploded.
And when the lights just went out, I could not see more than 2 or 3 feet. And I thought, my God, if it was a nitrate explosion, I'll probably lie right here and be burned to death.
He got up, looked over his shoulder at the burning tanks of benzene, and ran for his life.
Passed a car, which 2 people had been decapitated. And then I passed one of the 2 little planes that had been flying around overhead, came down along the path that I took up to town.
I'm sure all of that glass came into us, and I must have gone like this. And so my arm was injured all in here.
Mary Hunter was also in the Monsanto plant. To this day, she still has shards of glass in her body.
I had it cut out of me, but luckily it had lead in it. And therefore when they x-rayed it, they could find the glass.
Before the explosion, hundreds of people were on the docks, including Herb Metzger.
I had turned to walk away. I had my back to the explosion, but the force hit me in the back, and it sort of just, I don't know, I would say it picked me up, but it moved me forward 20 or 30 feet.
Suddenly, pieces of the ship were falling all around him. He crawled under a car.
A couple of pieces hit the car. I could feel it, you know, and it jarred, but nothing hit me.
Here comes another explosion.
But pieces of metal did hit the High Flyer, a second ship loaded with ammonium nitrate. Efforts to tow the burning ship out to sea failed, and 14 hours later, it exploded. The fires burned for days. Nearly 600 people died, and 5,000 were left injured or homeless. Those who survived helped each other.
We had to pry some folks out that had telephone poles, in fact, I guess, or some kind of big poles blown across them. They obviously were crushed, you know. It was not a nice sight, but kind of steeled myself to it for a while.
Even after the dead were buried, many survivors never talked about it again. But over the half-century since the explosion, they rebuilt their lives and their city. That must have been a hard thing to do, with so many memories around. Charles Hadlock, 11 News, Texas City.
All right, so we have this reaction. This is obviously a dangerous combination, right? You got to be very careful when doing reactions like this. Anyway, mix it together and see what happens. Hopefully, under controlled circumstances, we're going to form some aluminum oxide. And so the aluminum is going to be oxidized to its max, which is Al3+ here. Also some aluminum chloride. Again, aluminum goes from 0 to 3+ here. Some H2O liquid and some nitrogen gas. So, you know, when you combust the nitrogen-containing things, it depends on how much oxygen is present and what kind of pressure and heat you have. You can make different things. Just like combustion of methane, can yield different products. And so in a lot of chemistry, you know, it's kind of hard to predict theoretically, you know, what the products are. Here it's not so hard because aluminum, when you oxidize that, it's going to go to aluminum 3+, and then you got to figure out what anide you have. But, you know, why did the oxygen go there? Why didn't some of it go here? Why didn't we form some NOx in this? And it just depends on the conditions. And so a lot of these you just mix together and see what happens. You do it small scale, of course, because you don't want a big explosion in case it does react violently. All right, now we got to balance this. So balancing this, you know, some tricks are which species or species do we want to save for last? Well, when we have something like this, we want to save aluminum and nitrogen for last. Because if we change the coefficient of aluminum or nitrogen, it's not going to upset any other element. Right? So we save that. And we usually do the most complicated species first, like this. And so let's go ahead and try to balance it. What should we balance first? Maybe the nitrogen, the hydrogen, the chlorine, the oxygen, which one? Let's see. Maybe not the nitrogen, because the nitrogen is, here, single element. We're going to adjust that later, right? The hydrogen would be a good choice, because hydrogen ends up in H2O, which will screw up the oxygen, or the chlorine. The oxygen occurs in two different compounds, so let's not bother balancing that. And so it's going to be either the hydrogen or the chlorine. Which one do you want to start with? The chlorine? Okay, let's start with the chlorine here. And so over on the left we have 1 chlorine, on the right we have 3 chlorines. So we just need to do this. Once we change the coefficients, that's going to fix everything else. We don't want to change that. And so we have 3 chlorines here, we got 3 chlorines here. I don't want to change AlCl3 because that'll mess up the balance that we just did with chlorine. All right. Then what? Well, that's going to fix our nitrogen. We can't change the nitrogen, so now we've got to balance the nitrogens. So we've got 3 nitrogens here. We have 2 nitrogens here. And so how would I balance it? The easy way to do it is just to do 3 halves. If I do 3 halves and 2, the 2's cancel and gives me 3 nitrogens. So we have 3 nitrogens there, now 3 nitrogens here. Just leave it as a fraction. Okay, now I want to balance the hydrogens. The oxygens are going to be more complex because of 2. So balancing out the hydrogens, I have, 12 hydrogens there, so I'm going to need 6 waters here. So I don't want to change water, I don't want to change nitrogen. Now I got to balance out the oxygens, because this 6, I have a fixed number here of oxygens, but this is variable right here. And so I'm going to have 3 times 4 is 12 oxygens here. So I got 6 oxygens here. 6 plus 6 will give me 12. So I'll just multiply this one by 2. So that's 6 and 6, 12 oxygens. That leaves me with 4 aluminums plus 1, which would be a total of 5 aluminum. So we've balanced that. And so this stoichiometry problem is, what is the minimum mass of ammonium perchlorate consumed per kilogram of aluminum by the reaction of ammonium perchlorate and aluminum? They tell us the hint here to balance this. Pretty much, we didn't follow this order, did we? But that's all right. I don't know why they did this one. Okay, so we're going to go from kilograms of aluminum. And so just a straightforward, this is, after balancing it, becomes a pretty straightforward stoichiometry. We go from kilograms of aluminum to grams of aluminum, from grams of aluminum to moles of aluminum. When we use molar masses, we're going to use 2 decimal places. Use 2 decimal places for molar masses. Except for atomic hydrogen, H. H, we're going to use 3 decimal places, so we'll call it 108. That'll give us 4 sig figs. We want 4 sig figs. And H2. H2, we're going to use 3 decimal places again, so this is going to be 101.6. 101.6. Right? We aren't going to use 108 if we're dealing with something like ammonium perchlorate. You know, if we go to ammonium perchlorate, we have 1 nitrogen. We use 2 decimal places because it's easy to remember. For example, nitrogen I have memorized, 1401. You've done it enough times. 4 hydrogens. Hydrogen I have memorized to 2 decimal places, 101. And so 101 times 4 gives me 404. Here it's okay, 2 decimal places, because in the end, we're going to end up with 4 sig figs. Chlorine, I have memorized too, 35.45. Oxygen, I have memorized at 16. 4 times 16 will be 6400. And so calculating molar masses is quick if we just go 2 decimal places, except for these scenarios here. Sometimes we'll need more. Yeah, sometimes we'll go 5, like 10079, not 108. All right, so from moles of aluminum, and we want to get to ammonium perchlorate. And so moles of aluminum to moles of ammonium perchlorate. Moles of ammonium perchlorate to grams of ammonium perchlorate. And then grams to kilograms of ammonium perchlorate. And so just a pretty straightforward basic stoichiometry problem here. Okay, we're going to do another one here. Or look at another one, just set it up. Let me find that. Actually, we aren't going to do another one. We're out of time. So we'll stop for today and then continue.